Good evening, everyone. Now we are going to discuss about our continuation of oscillators. Okay. So in our oscillators, in last class, we have discussed about what is meant by oscillator. Okay, and what are the different types of oscillators. At the same time, we are also discussed about operation and construction of Hartley oscillator as well as Colpitts oscillator. Okay. So before going to discuss about the frequency response of Colpitts oscillator, first I would like to discuss you last class topics. Simply, I would like to revise the last class topics. Okay. So in last class we are already discussed about oscillator. So what is meant by oscillator? It is an electronic device which is used to increase the strength of weak signal. And what are the conditions to work out one circuit as an oscillator or one amplifier as an oscillator? What are the conditions? It must and should satisfy the condition of Barkhausen criteria. What is meant by Barkhausen criteria? The total phase shift around the circuit is equal to 0 or 360 degrees, and the magnitude of product of loop gain must be is equal to 1. What are the two conditions? Total phase shift around the circuit is 0 or 360 degrees, and the magnitude A beta is equal to 1. So these are the two conditions here we are using to produce the oscillations or to work one circuit as an oscillator. That must and should satisfy these two conditions. What are the two conditions? The product of loop gain must be is equal to 1, and the total phase shift around the circuit is equal to 0 degrees or 360 degrees. Okay. And while coming to the classification, the amplifiers are classified into two types majorly based on the waveform is produced, whether it may be sinusoidal or non-sinusoidal. According to that, the oscillators are basically classified into two types. If the oscillators are used to produce the sinusoidal waveforms, are again classified into LC oscillators as well as RC oscillators. Okay. In LC oscillators, the tank circuit is made with inductive and capacitive circuits. In LC circuits, tank circuit is made with inductive and capacitive circuits. So here of three types are there. Single tuned is there, Hartley oscillator is there, Colpitts oscillator is there. So in single tuned circuits, one inductor is connected in parallel with one capacitor, that makes tank circuit. And while coming to the Hartley oscillator, two inductors are there, they must be connected in series, and these two inductors are connected in parallel with capacitor. Okay. And while coming to the Colpitts oscillator, two capacitors are connected in parallel with the inductor. So that is only the difference. So in single tuned, one inductor is connected in series with one capacitor, and in Hartley oscillator, two inductors they internally connected in series and are connected in parallel with the capacitor, and in Colpitts, two capacitors and one inductor is there. Finally, in all LC oscillator, the tank circuit is made with inductors and capacitors. Okay. So these LC oscillators are used to produce sinusoidal waveforms. And while coming to the next one, non-sinusoidal oscillators, these are in sinusoidal one more group is there, that is RC oscillators. So in RC oscillators, the tank circuit is made with resistor and capacitor elements. Here three types are there. RC phase shift oscillator is there, and also Wien-Bridge oscillator is there, and also resistive oscillator is there. And see here, while coming to the non-sinusoidal oscillators, okay, according to the frequency, ultra high frequency, very high frequency, radio frequency, audio frequency is there. And while coming to the non-sinusoidal, Schmitt triggers, okay, and square wave generators, pulse generators, all these are comes into the non-sinusoidal. And according to the frequency produced by the oscillators, these are of audio frequency, radio frequency, video frequency, ultra high frequency, and very high frequency. In audio frequency, the oscillators produce the oscillations. The frequency of produced oscillation is lies in between 20 Hz to 20 kHz. In radio frequency, the oscillations produced having the frequency range is above 20 kHz. In very high frequency, it's some gigahertz, and in ultra high frequency above gigahertz also. So like this, so till full frequency the oscillators are available. So this is about what the classification, main classification of oscillators. And in our last class we are also discussed about the requisites of oscillators. To construct one oscillator, what it requires, what are the requirements of an oscillator. Okay, while coming to the requirements, not conditions, requirements, it requires three circuit. One is amplifier circuit, other one is tank circuit, third one is feedback network. So how many number of circuits it requires? Means how many number of circuits an oscillator requires to work it as an oscillator. Okay, it requires amplifier and also feedback network and also tank circuits. So here already obviously we know amplifier is made with transistor circuit. It is a RC coupled amplifier and it containing potential divider, biasing network R1 R2 for biasing and stabilization. Coupling capacitors also there. Cin is used for to block the DC signal and only attach AC signal. Emitter bypass resistor and capacitor is there. They provide slow reactance path to the signal. Okay, this is the history of amplifiers are used in oscillators. And while coming to the tank circuit, generally the tank circuit in amplifier made with inductors and capacitors. Sometimes instead of inductors we are also using resistors. Okay, and what is the function of tank circuit here? It is called frequency determined circuit. Based on the elements used in the tank circuit, the frequency of produced oscillators may increased or decreased. So that's why this tank circuit is called frequency determined circuit. Okay, what is meant by tank circuit? It is made with inductors and capacitors. Sometimes it is also made with resistors and capacitors. But it is also called what? Frequency determining circuit. Why it is called frequency determining circuit? So whatever the components we are used here are used to determine the frequency of the produced oscillations. And next one is what? Feedback circuit. So here we are going to use positive feedback in oscillators. So to connect that fraction of output back to the input is called feedback. So to connect that, here one network is used, that is called feedback network. Here the feedback network is generally made with either resistor or like that. Okay. And see here we are using positive feedback. So while coming to the positive feedback, if the input voltage is in phase with the feedback signal, then the feedback is called positive feedback. If the input signal is in phase with the input signal, then the feedback is called positive feedback. So these are what requirements we are already read in our last class. And in last class we are also discussed about two oscillators. First one is called Hartley oscillator and other one is called Colpitts oscillator. See here, while coming to the construction of oscillator, the circuit is generally like this. It consisting of two inductors are connected in series manner and are connected in parallel with capacitor, and it is connected back to the transistor. L1, L2 and C, here this will form the tank circuit, and here it is the amplifier circuit, and this form the feedback network. Okay, so in Hartley oscillator, the tank circuit is made with two inductors and one capacitors. So here two inductors are connected in series manner and both inductors are connected in parallel with the capacitor. And here also the potential divider biasing network is there, that is made with resistor R1 and R2, and it will provide proper biasing and stabilization. While coming to the biasing, if emitter base junction is in forward biased condition and the collector base junction is in reverse biased condition, then transistor operates in active region. And now the operating point is independent of temperature variations and transistor parameter variations. If it depends on temperature variations, while increasing the leakage currents, automatically the temperature also will be increased, so that self-destruction may be occurred. So this reason here we are using potential divider bias network. And here the transistor acts as an amplifier. It will provide 180 degrees phase shift to the given input signal. But here one condition is there: to produce oscillations, the circuit must and should satisfy 360 degrees phase shift. So 180 degrees is came from here our transistor, and the remaining 180 is came from our tank circuit. So why we are getting 180 degrees from this tank circuit means the voltage must be reach the inductor. Now the inductor going to start charging, then it slowly discharged. After it discharged, the inductor too starts charging. After fully charging, it's again discharging. Next, this voltage must be charged by the capacitor. The capacitor fully charged first, then it is discharged. So in this way, charging, discharging happens. So finally it would like to reach the base of the transistor. So 180 degrees phase shift is came from the transistor and further 180 is came from the tank circuit. The total circuit will satisfy the 360 degrees phase shift. So this is about the operation of Colpitts oscillator. So initially the input signal is applied across the base of the transistor and it must be amplified, and 180 degrees phase shift signal is given to the tank circuit, and it is given to the tank circuit through the base of the transistor. So inductor 1 and 2 are connected to the capacitor. So finally 360 degrees phase shift is satisfied and the circuit start produce oscillations, and the frequency of oscillations will be depends upon the inductor and capacitor. Simply it is F is equal to 1 by 2 root LC. So here L means LT. So why we write LT means total inductance. So the total inductance may be L1 plus L2 plus R minus 2M. It is L1 plus L2 plus 2M for series connection of inductors, and it is L1 plus L2 minus 2M for series opposition inductors. If the connection is series aiding, then that is L1 plus L2 plus 2M. If the connection is series opposition, that gives L1 plus L2 minus 2M. And already we know the capacitance value. before going to getting the oscillations, theoretically we calculate with help of the inductor and capacitor values. So this is about what? Hartley. And now today's topic is expression of Colpitts oscillator. So once see the diagram of Colpitts oscillator tanks. So here the input voltage is applied through the capacitor and it having the circuit like this. In Hartley oscillator, 2 inductors and 1 capacitor is used, but in Colpitts oscillator, 2 capacitors and 1 inductor is used. Okay, see here, now here it is the tank circuit, okay, and it is the amplifier circuit and it is the feedback circuits. The requisites will be satisfied. Amplifier is there. This is the amplifier. And it is tank circuit and it is feedback network. So here same, the amplifier is able to produce 180 degrees phase shift and the tank circuit is able to produce remaining 180. Total 360 degrees must be achieved and the circuit start to produce oscillations. So in frequency response of Colpitts oscillator, F is equal to 1 by 2 roots LC. So here C indicates CT, total capacitance. Cause of capacitors are connected in series, total capacitance CT is equal to C1 C2 by C1 plus C2. So this is a mathematical expression for frequency response of Colpitts oscillator. So these are the different topics we are discussed in our last class. So now we are going to discuss about the mathematical expression of frequency of oscillations in Colpitts oscillator. So see here, while coming to the equation, first we would like to write the inductive and capacitive reactance is indicated with x1, x2, x3. So here x1 indicates inductive reactance, x1 indicate what? Inductive reactance, x2 indicate capacitive reactance of capacitor C1, x3 indicates capacitive reactance of C2. So the total reactance in the circuit is equal to 0 to calculate the frequency. Why? Because total phase shift around the circuit is equal to 0. So first we would like to write the reactances. Inductive reactance is indicated with x1. Capacitive reactance of capacitor 1 is indicated with x2 and its second capacitor is indicated with x3. And total reactance in the circuit is equal to 0. So that here we write x1 plus x2 plus x3 is equal to 0. But inductive reactance is indicated with j omega L1. Inductive reactance is indicated with omega L1 and capacitive reactance are indicated with 1 by omega C2, reciprocal of omega C. So finally j omega L1 plus 1 by j omega C2 plus 1 by j omega C3 is equal to 0. And see here j omega L1 minus 1 by j omega C2 means by taking j out numerator, then j omega L1 minus j by omega C2 minus j by omega C3 is equal to 0. Omega square L1 is equal to 1 by C2 plus 1 by C3 is equal to C2 plus C3 by C2 C3 while taking the common terms. So here omega is equal to what? From the above equation, under root of, why? Because omega square L1 is equal to C2 plus C3 by C2 C3. So here omega is equal to what? C2 plus C3 by L1 C2 C3. So see here omega square is equal to C2 plus C3 by L C2 C3. But our frequency equation is what? 1 by 2 pi under root of C2 plus C3 by L1 C2, C3. So this is the mathematical expressions of our frequency response of Colpitt's oscillator. And see here, our next topic is crystal oscillator. What is our next topic? Crystal oscillator. So see here, why we are moving with crystal oscillators? Already LC is there, Colpitt's is there. So crystal is going to give very high frequencies compared to the Hartley and Colpitt's. So in crystal oscillators, quartz crystals or Rochelli sheets are used in the tank circuits. So what is the principle used in the tank circuit here is, so here we are using quartz crystal. So that quartz crystal principle is piezoelectric effect. What is the principle involved in the quartz crystal? Piezoelectric effect. If we apply the mechanical vibrations applied across it, it will able to produce electric currents or voltages. If we apply the electric voltages or currents, it produces mechanical vibrations. So this phenomena is called piezoelectric effect. So this quartz crystal based on the principle of piezoelectric effect. Is it clear what is meant by piezoelectric effect? If we apply the electric voltage across the crystal, it provides mechanical vibrations. Or otherwise, if we apply mechanical force or pressure, it able to produce electric vibrations. Based on this principle, the crystal oscillator will work. So the name of the principle is called piezoelectric effect. And see here, this is the diagram of quartz crystal. So here two metallized electrodes are used. If I apply the electric voltage or current, it produces mechanical vibrations. Or if I apply mechanical force across the crystal, it able to produce electric current. And this is the equivalent circuit. Means quartz crystal is equal to 2 capacitors and 1 inductor. 2 capacitors and 1 inductors, how acts like the same way the crystal also operates. Is it clear? This is the equivalent circuit of crystal. So whatever I explained, that is there in the slide 1C. Here the quartz crystal exhibits a very important property known as piezoelectric effect. Already I told this. What is meant by piezoelectric effect? When mechanical forces applied here, it will produce electrical vibrations. If we apply electrical voltages, it will produce mechanical vibration. See here, when mechanical pressure is applied across the faces of the crystal, a voltage which is proportional to the mechanical pressure appears across the crystal. The voltage causes distortion in the crystal. The distorted amount will be proportional to the applied voltage, and also an alternating voltage applied to the crystal, it causes to vibrate its natural frequency. Finally, the whole meaning is what? By applying mechanical pressure or force, it will produce electrical vibrations. And if we apply the electric voltages or currents, it able to produce mechanical vibrations. So this is about what? Piezoelectric effect. This mechanism is called piezoelectric effect. And see here, when the crystal is not vibrating, simply it is equivalent to a capacitance. Because one fact here we reveal, two metals are separated by dielectric medium. quartz crystal is looking like this. One metal plate, other metal plate, here crystal is there. In between these two some space is there. So clearly it's looking like two metal plates are separated by dielectric media so that it works like a capacitor. This capacitance is known as mounting capacitance. When a crystal starts vibrations, it is equivalent to RLC series circuit. Therefore, the equivalent circuit of vibrating crystal is RLC series circuit shunted by the mounting capacitance Cm as shown in below figure. So when a crystal starts vibrate, it is equivalent to RLC series circuit. If it is not vibrating, it is equivalent to capacitance. If it is in vibration condition, it is equivalent to RLC circuit. Is it clear? If the crystal is not vibrating, it is equal to a normal capacitance. Why? Because here two metal plates are separated by this dielectric media. And if it is in vibration condition, it is equal to RLC series circuit. So therefore, the equivalent circuit of vibrating crystal is RLC circuit shunted by the mounting capacitance Cm. And see here, one key point is there here. When crystal is vibrating, L is the electrical equivalent of crystal mass. Means under crystal vibration, it is equal to RL circuit na. So here L is the equivalent of crystal mass. And C is the electrical quantity of elasticity. R is the equivalent of mechanical friction. Is it clear? Under vibration, it is equal to R, L, C series circuit. So why under vibration it is equal to RLC circuit means under vibration it produces mechanical friction. So here R indicates the mechanical friction and here L indicates the crystal mass and C indicates the equivalent of elasticity. So finally the crystal oscillator under vibration acts like an RLC series circuit. RLC series circuit. Okay. So now we are using this crystal to produce the oscillations in circuit. See, one second. So this is the circuit of crystal oscillator. Here in tank circuit, it's simply like say Colpitz's oscillator. In Colpitz's oscillator, here this inductor is replaced with the crystal here. See here, two capacitors are there, but inductor in Colpitz's oscillator is replaced with the crystal. Except that everything is same. What it contains? Potential divider network is there, that is made with resistors R1 and R2, and coupling capacitor C in capacitor is there to connect feedback voltage back to the base of NPN transistor, and emitter bypass resistor is there to provide low reactance path to the signal, and chokes are there to provide the high frequency. In tank circuit, it is almost equal to that of Colpitz's oscillator except crystal. So in Colpitz's oscillator, in place of crystal, there we replace it with inductor, but here we are using crystal. So this is the construction of crystal oscillator. Okay. Here the potential divider network R1 and R2 is used for providing transistor biasing and stabilization. Already I said that it makes operating point independent of temperature variations and transistor parameters. Cause of that, emitter base operates in forward bias condition and collector base operates in reverse bias condition. That makes the transistor going to operate in active region. So when the transistor operates in active region, now the operating points independent of temperature variations and transistor parameter variation, so that it will protected from the thermal runaway. This is the main theme of potential divider network R1 and R2. And here this input capacitor Cin is used to connect the feedback voltage back to the base of transistor or amplifier circuit. And why it is used, why we are unable to connect it directly means, it allows the pure AC signal and block the unwanted DC signal. For that purpose mainly it is used. That's why it is also called blocking capacitor. And while coming to the tank circuit, here the tank circuit is able to produce 180 degrees phase shift and our amplifier will produce 180 degrees phase shift. Total 360 degrees phase shift is achieved and now the circuit start to produce oscillations. So this is the principle involved in crystal oscillator. So when the supply voltage VCC is switched on, few amount of voltage will be produced cause of amplifier and it must be given to the tank circuit cause of capacitor charging and discharging. Quartz crystal going to develop mechanical vibrations and it will produce 180 degrees phase shift and the amplifier circuit produce 180 degrees phase shift. Total 360 degrees phase shift will be produced in the circuit. So finally so now it is able to produce the oscillations. Okay, so this is the construction and operation of crystal oscillator. So it is briefly discussed in the slides also. Once I would like to check the slides. So see here the practical transistorized crystal oscillator is shown in figure. The circuit is same as Colpitt's oscillator. Already I said this to you. Okay, and here it is replaced by the crystal. Inductor is replaced by the crystal, and here the crystal will act as an inductor and the resonant with 2 1C and C. And see the oscillating frequency lies in between the series and parallel resonant frequency. The positive feedback is provided by the capacitor voltage divider network C1 C2 and the resistances R1 R2 provides DC bias, while the capacitor emitter bypass capacitor CE provides low reactance path to the signal, and RFC provides isolation between the AC and DC operations. Where we connect RF is connected across the collector of the transistor, and C means coupling capacitor C in 19cc are used to allow only the selective frequencies and block all other frequencies. Okay, so now it is the working of crystal oscillator. Already it is also explained with the help of diagram, but once you check the slide. So see here, the total phase shift of 0 and 180 degrees is produced by the, means the total phase shift of 180 degrees is produced by the transistor, and further phase shift of 180 degrees is produced by the capacitor voltage. Total how much we need? 360 degrees. So among 360, 180 degrees is produced by transistor, and the remaining 180 degrees is produced by capacitive voltage divide network. And the circuit will oscillate at a frequency, that frequency is lies in between the series and parallel resonant frequency. It can be noted that the oscillator frequency is essentially determined by the crystal and not by the rest of the circuit. In crystal oscillator, the frequency is must and should determined only by the crystal, not by the other components in the circuits. Is it clear? So this is about what? Quartz crystal oscillator construction as well as operation. And see here, while coming to the advantages, wide varieties of advantages are there while using with crystal oscillator compared to the Colpitts and Horsley. The tuned circuit oscillators are good for generating high frequency oscillations. What is the main reason of designing crystal? It will generate high frequency oscillations and good frequency stability, and the waveform can be obtained from RC phase shift or phase shift oscillators. And the crystal oscillators have high frequency stability also. It will produce high frequency oscillations. At high frequency also the circuit becomes stable, means the frequency, for example number of cycles per second are 10 at 30 Hz, it maintains 10 for 50 Hz also, that because stability. It produces high frequency oscillations, and these high frequency oscillations are in stable condition. Now the crystal oscillator is possible to obtain very high, precise and stable frequency oscillations, and it has high frequency of operation. It has very low frequency drift due to change in temperature and other parameters. The Q is very high. Here Q indicate what's operating point. And it has automatic amplitude control. The amplitude must be automatically increased or decreased, depends upon the mechanical pressure applied to it. Okay, what are the advantages? The tuned circuit oscillators are very good for generating high frequency oscillations and good frequency stability, and the waveform can be obtained from RC phase shift oscillators simply like that. And the crystal oscillators have very high frequency stability. The crystal oscillator is possible to obtain very high, precise and stable frequency of the oscillations. It has high frequency of operation. Okay, and while coming to the other advantage, it has very low frequency drift due to change in temperature and other parameters. And the Q is very high. It has the automatic amplitude control. It has the automatic amplitude control. And this is about what? Our applications of quartz crystal oscillators. And while coming to the next topic, see here, what are the reasons for instability in oscillators? In various oscillators, the circuit becomes unstable. Now, what are the reasons to produce the instability? So here inherent variations of transistor parameters. Why the oscillations are in unstable condition means cause of variations of transistor parameters. What is the main reason for instability of oscillations? Variations of transistor parameters. And second one is variations in supply voltage. Maybe cause of variations in supply voltage also will affect the stability of oscillations. And also the temperature variation will affect the stability. Temperature variation will also affect the stability. And inter-element capacitances, stray capacitances also will affect the oscillations. Finally, mechanical vibrations also will affect the stability. So first one is inherent variations of transistor parameters. Second one is variations in supply voltage. Third one is temperature variations in output load. Fourth one is inter-element capacitances and stray capacitances. Fifth one is mechanical vibration. And last one is overheating of the components and devices in the circuit. Why overheating means? Cause of leakage currents, junction temperatures and currents must be increased. Why? Because all these are semiconductor. If temperature increased, ICBO, ICEO, leakage currents increased. When leakage currents are going to increase, more amount of heat will be produced. Cause of that self-destruction is occurred. Is called what? Thermal runaway. And last one, imperfect tapping of the coils. Means cause of improper tapping also, improper connecting also, the instability in oscillators will be occurred. And what are the remedies? Cause of temperature variations and power supply variations and due to the temperature parameters and improper tapping, there is an instability. So by proper tapping, the circuit becomes stable. And by maintaining constant temperature, the circuit becomes stable. And maintaining constant parameters, circuit becomes stable. And see here the frequency instability in oscillator can be avoided by taking supply voltage regulations can be overcome by using RPS. I said one reason, cause of variations in power supply also. So variations in power supply can be changed by using regulated power supply. And frequency stability can be increased by using temperature compensation technique. Why? Because cause of temperature variations also, circuit becomes unstable. So the temperature variations can be compensated by using temperature compensating techniques. And the loading effect can be minimized by using buffer stages. And the effect of changes in the inter-element capacitances can be neutralized by adding a swamping capacitor across the offending elements. And the frequency stability of oscillator are also increased by using tank circuits with high Q. And already I said improper tapping also may affect the stabilization. So you must and should tap properly the all coils. And the circuit must be isolated from the source of mechanical vibrations. Now the temperature controlled chambers are used to minimize the temperature effects. So these are the different remedies to provide the stabilization. So now what is the last topic? Compare RC oscillator and LC oscillator. So while coming to the RC oscillator, only cause of using resistors and capacitor, the frequency is very less. So it is suitable for medium and low frequencies. And the frequency of oscillations is depends upon the values of resistor and capacitor. But in LC oscillators, the frequency of oscillations is depends upon the value of inductor and capacitor. And here these are preferred as high frequency. LC always preferred for high frequency, RC preferred for low frequency. The examples of RC oscillators are RC phase shift and Wien-Bridge oscillators. And the examples of LC oscillators are Hartley oscillator, Colpitts oscillator and Clapey oscillator. And in RC oscillator, the stability is very less, poor frequency stability is there. But in LC oscillator, compared to the RC oscillator, they become somewhat stable. So here it is used for RC oscillators are used for low and medium frequency only, but LC oscillators are used for high frequency, means are used in TVs, radios, etc. So today's topics are what? Frequency response of Colpitts oscillator, what is meant by quartz crystal oscillator, what is the principle involved, what is meant by piezoelectric effect and how it works, and what is the reason for using quartz, and what are the reasons for providing instability, what are the remedies to avoid the instability, and what is the difference between RC and LC. So now I would like to conclude the class. We will meet you in next session.